Airplane navigation is just an extension of relative motion. In the previous examples, we used relative motion to solve river crossing type questions where a boy was swimming across a river where there was a current that was pushing him off course. The exact same concept applies to airplanes. The only difference, of course, instead of water, we have wind. The terminology also remains the same. So starting off with the concept of heading. The heading is the direction or the orientation of the nose of the plane. Basically, it is the direction that the plane is physically pointing in terms of compass directions. However, the heading is not necessarily the direction in which the plane is going to move in comparison to the ground itself. So the heading describes the motion of the plane within the air or the wind. So with respect to the wind, the heading applies to the direction that the plane is flying through the wind itself. Now, of course, if there is no wind, the heading and the bearing will be exactly the same. Or if the wind and the plane's heading are either parallel or anti-parallel. The bearing is again the direction of the resultant velocity, specifically with respect to the ground. So how the plane moves with respect to the ground is indicative of the bearing of the plane. So when we look at this particularly simplified diagram here, in this diagram, our plane is pointing, for the sake of argument, north. So our heading would equal north in this case. Now the wind is blowing to the east, as you can see here. So the resultant, this vector here, that is the path that the plane is actually going to fly, and that would be the bearing. So this angle in here, and we'll call it theta r for the resultant, that angle there is associated with the bearing. So the bearing would be equal to something like north and whatever, I'll make up some number, 25.0 degrees to the east. Now, of course, that angle is entirely dependent on the relationship of the velocities between the wind and the plane. And in the sample problems that we're going to take a look at, we're going to consider those very things. Other big ideas. The concept of airspeed. The airspeed is not the velocity. Technically, it's the magnitude of the velocity. The magnitude of the velocity of the plane with respect to the air or the wind. Or in this notation, that would be the magnitude of the plane's velocity with respect to the wind. The ground speed is associated with the velocity of the plane with respect to the ground. So this would be the magnitude of the plane's velocity with respect to the ground. In terms of wind direction, the way winds are usually reported is in a way that describes their direction from which they come. So for example, when we say an easterly wind, that means winds from the east. That means the wind is moving to the west. Northerly means winds from the north, which means they are traveling south. Southerly winds are from the south, which means they are moving north. And finally, westerly winds are from the west, which implies that they are moving towards the east. Okay, so let's start off on the two sample problems, example 1 and 2 below. So organizing the solution into the GRFS format, we're going to be stating our givens required to find the formulas used. Now, generally speaking, the formula section is more so for the student's benefit in terms of reviewing later. It's not as critical. The most critical components are the detailed given section required to find and the solution. But the formula section is also helpful, especially when you are reviewing for the future assessments and whatnot. Okay, so let's start off with giving a read of the very first line. So a plane heading due south at 700 kilometers per hour. As you can see, we're to 3 sig figs here. So when we see this heading due south, the key word is heading. And when we see the word heading, that actually must be describing the plane's velocity with respect to the wind. So this is the plane's velocity with respect to the wind. Flying through a westerly wind blowing at 150 kilometers per hour. So the wind is always measured with respect to the ground. So a westerly wind means that it's blowing from the west, therefore traveling to the east. So this represents the wind's velocity with respect to the ground. So we'll start filling in our given section. The plane's velocity with respect to the wind is 700 kilometers per hour north. The wind's velocity with respect to the ground is 150 kilometers per hour east to 3 sig figs, as you can see. So part A, we're trying to find the plane's ground speed in kilometers per hour. So that means in part A, we're looking for the magnitude of the plane's velocity with respect to the ground. In part B, we're asked to find the plane's velocity with respect to the ground in kilometers per hour. Well, in part A, we've already found the ground speed. So what's different about part A and part B? Part B, we're asked to find the velocity, which means we're looking for the angle. So in part B, we're trying to find the plane's velocity with respect to the ground. So really what we're looking for is the bearing. Actually, we'll be a little bit more specific. Theta of the bearing. Incidentally, that will be the theta of the resultant. In part C, it's asking how far off course does the wind take the plane over 2 hours in kilometers. All right, so first of all, we have a new number, and our new number has to do with the amount of time. So for part C, time is equal to 2.00 hours. Now, if you notice, we're not actually using meters per second in this case. We're working with kilometers per hour, kilometers, and hours. So we're just going to leave it that way because the question's asking us to use kilometers per hour, and therefore it's unusual. We usually in physics work with meters per second and seconds, but when it comes to airplane navigation, it's really a more appropriate scale to be working with kilometers and hours. So what does it mean by how far off course does the wind take the plane over the 2 hours? What is it actually asking us? What it's technically asking is basically how far the wind has traveled in that amount of time. Because since the plane is flying through the wind itself is carrying the plane along off course. So however far the wind travels in those 2 hours is precisely how far off course our plane will fly during that duration. So what we're really looking for is the wind's displacement with respect to the ground. Part D, what heading must the plane maintain in order to travel due north with respect to the ground? Okay, so now something has changed here. In parts A through C, we knew that the heading was due north, but the question is now asking what the new heading is going to be in order to travel due north with respect to the ground. Translation, that means that we have a desired bearing of due north, which means we have to calculate what heading will produce that desired bearing under these wind conditions. So in part D, we're looking for theta of the new heading, which means that in part D, we've now gained some information. We now know the bearing. So what that means is we now know that the plane's velocity with respect to the ground, we do not know its magnitude. No idea what its magnitude is. But what we do know is that we have a heading of due north now. So what's happened is we've gained information about our resultant. Our resultant is now moving north, but that means we've lost something. And what we've lost is the original heading. So now the plane's velocity with respect to the wind, the magnitude is still going to be 700 kilometers per hour to 3 sig figs, of course, but the heading is now unknown. And that is what we are trying to find. And then finally, what would be the plane's ground speed in part D? So for part E, we're now recalculating the magnitude of the plane's velocity with respect to the ground. Starting the solution for part A. So we're looking for the plane's velocity with respect to the ground, or the magnitude, I should say, of the plane's velocity with respect to the ground. So before we can do that, the first thing we need to do is we need to come up with our vector equation. So the plane's velocity with respect to the ground is equal to the plane's velocity with respect to the wind plus the wind's velocity with respect to the ground. Notice the order. We start with a P, we start with a P. We end with a G, we end with a G, and then we have our W sandwich. Okay, so that's our vector equation. But again, this notation is cumbersome. So we're going to give it the short names. So PVG is our resultant. PVW, I'm going to call that my vector A. And WVG, I'm going to call that my vector B. So what I'm going to do now is I'm going to go back up into the given section, and I'm going to apply these short names to the values given in the given section. So our PVW, that is equivalent to our A. Our WVG, that is equivalent to our vector B. PVG, that is equivalent to our resultant. And then this again will be our vector A, but for part D. So we're looking for the magnitude of our PVG or the magnitude of the resultant. And since we're looking for the theta of the bearing, that's the theta R that we're looking for. Now that we have the vector equation, the next step is to draw the vector diagram. So with the vector diagram, I just draw it with the short names. So we start off with our vector A, which was 700 kilometers per hour north. Now I've labeled the magnitude and I haven't bothered with the units just so we don't make the diagram too cumbersome with excessive notation. Vector B is the wind's velocity with respect to the ground, and that's a magnitude of 150 kilometers per hour. And this is our resultant, which refers to the plane's velocity with respect to the ground. And our theta R is the direction of our bearing in this case. In this particular case, I didn't actually draw the compass rose. And the reason why I didn't bother drawing the compass rose in this case is because vector A is already sitting on the north line. So there really is no need to draw the compass rose in this particular case, because when we eventually solve for theta R is already sitting against the north line. So I didn't need to add that little extra. Finding the magnitude of the plane's velocity with respect to the ground, or the magnitude of the resultant. Well, to solve for the magnitude of the resultant in this case, since we have a right-angled triangle, and we know that it's right-angled because vector A is north and vector B is east, and that is absolutely implied to be a 90-degree angle. So using Pythagorean theorem works perfectly well. So what we get for the resultant, or the magnitude of the resultant, is 716 kilometers per hour rounded to 3 sig figs. However, if you notice in the line above it, I actually expressed the resultant in this form, 50 square root of 205. And the reason why is that this form of the value is better to use in future calculations than the second one. That is why I have a green check mark beside it. And the green implies that there is no rounding error that is added to it. Now I have this little convention that I use with the check marks. Now technically speaking, there is the potential that I could have actually just made a mechanical error. So this isn't actually green necessarily, I should say. But it is better than this one. So the other convention I often use, just to sort of distinguish in terms of quality of our results, I use the amber check mark to indicate that the answer is good, but proceed with caution because there is potential for error. And when we have additional error, I even make it a little bit dirtier, closer to brown, because that implies that we're getting further and further away from a top quality answer here. So with the 716 kilometers per hour, there is even more error because of the rounding. Now the 50 root 205 is correctly calculated, but again, the idea is that there is the potential for it. So really it's just an idea of communicating the potential error that you have in the numbers as we go along, because it's important to be cognizant of the fact that your calculations are subject to error, and the goal is to use the highest quality numerical values in your calculations as possible. So if we can avoid using found results, we do so. We try to work with the given information as much as possible because that gives us the most pristine data. but we'll just go back to our original convention. Looks prettier that way. I'll use the faded green. There you go. Okay, so next, now we're looking to find the bearing, or theta r. So in this case, to find theta r, best practices would be to avoid using anything to do with the resultant. Technically, 50 root 205 is perfectly fine to use because there's no rounding error in there. But again, it is subject to actual mechanical error. It's easy enough to make a mistake in the line above. Say, for example, you wrote down, instead of 700 squared plus 150 squared, you got confused and you wrote 750 squared plus 100 squared. It's easy to make these numbers. Or in your calculator, it's very easy to accidentally write 105 instead of 150. So again, because there's always a potential for error, we're going to avoid using that. So to find the the angle theta r, we're going to use tangent. And the reason why we're going to use tangent is because from the perspective of theta r, this is the opposite side and this is the adjacent side. So using tangent, we find that tan theta r is equal to the magnitude of b over the magnitude of a. So to isolate for theta r, that is the arctan, or tan inverse, of b over a, which gives us 12.09476. With all the calculator vomit, of course, rounding off to 3 sig figs, that gives us 12.1 degrees. And therefore, the plane's velocity with respect to the ground is 716 kilometers per hour north, 12.1 degrees east. And one other thing, I should probably put a bracket in there. Best practices. Part C. Now we're looking for the wind's displacement with respect to the ground. Let's clean that up a little. Okay, so to find the wind's displacement with respect to the ground, the realization we have to use is the fact that the wind is moving at a constant velocity of 150 kilometers per hour, which simply means we can use d is equal to vt, the constant motion kinematics formula. However, in this case, it's the displacement. So the wind's displacement with respect to the ground is equal to the wind's velocity with respect to the ground times the time. The wind's velocity with respect to the ground has a magnitude of 150 kilometers per hour over 2 hours, which gives us 300 kilometers. Therefore, the wind's displacement with respect to the ground is 300 kilometers to 3 sig figs to the east. Moving on to part D. In part D, we're trying to find the new heading. So in part D, our situations have changed as described in the given section. So what I'm going to redo is the given section in this part here so that it's a little easier to parse what we have to do. So we're trying to find the new heading, which is actually going to be our theta A. You'll see why in a moment. So let's start off with rewriting our givens. So our vector A, if you recall, that was our plane's velocity with respect to the wind, has a magnitude of 700 kilometers per hour, but an unknown direction. Our vector B, which is the wind's velocity with respect to the ground, that's 150 kilometers per hour, and it is east. And then our resultant, which is the plane's velocity with respect to the ground, unknown magnitude, but the direction is known, and that is north. Surprisingly, our vector equation remains the same. The plane's velocity with respect to the ground is equal to the plane's velocity with respect to the wind plus the wind's velocity with respect to the ground, where the plane's velocity with respect to the ground is our resultant, PVW, plane's velocity with respect to the wind, is our vector A, and the wind's velocity with respect to the ground, that is our vector B. What has changed is our geometry. So now we have to start off with a new vector diagram. And the issue, of course, is the fact that we don't know the direction of vector A. So usually when you draw the vector diagram, you start off with the vector A, but we can't because we don't know its direction. But we do know everything about vector B, and we know the direction of the resultant. So as a reminder, here are the order. You always start off with the vector or vectors you know everything about. In this case, we know everything about vector B. So this is our vector B with a magnitude of 150. Next, you then draw the vector for which you know the direction, and that is our resultant. Now, as a reminder, and this is key, and let's go to our first vector diagram. the relationship of the resultant with vectors A and vectors B is the resultant is head-to-head with vector B because vector B is the last vector in the vector equation, and it is tail-to-tail with vector A, which is the first vector in the vector equation. That is always going to be true. The resultant will always be tail-to-tail with the first vector and will always be head-to-head with the last vector. That being said, we know then that the resultant must attach head-to-head with vector B, and the direction of the resultant is north. That means there is only one way to draw this vector. We don't know its length, so we're just kind of guessing, but we do know that it is due north. So it's going to look something like that. Now, of course, the resultant should be a dashed line because it is an unknown magnitude. And then finally, drawing in vector A, there is only one way to do this. We know vector A attaches tail to tail with the resultant. And then, of course, it's going to terminate at the tail of vector B. So our vector A starts at the base of the resultant and attaches to the tail of vector B. And this angle in here, that is your theta A, and that is the heading that we will be looking for. And we know vector A has a magnitude of 700 kilometers per hour. Based on the diagram, to find theta A, we can use the primary trig ratios because we definitely have still a right angle triangle, and that's because vector B is at right angles to vector R. But this is very, very, very important for us to understand here. Vector R is no longer the hypotenuse. So vector B is the opposite side, and vector A is the hypotenuse. Vector R happens to be the adjacent side. Therefore, to solve this problem, to find theta A, it's not going to be the tan function. In this case, it's going to be sine. So sine theta A is equal to the magnitude of vector B over the magnitude of vector A. Theta A is equal to the arcsine or sine inverse of B over A, which is the arcsine of 150 over 700, which gives us an angle of 12.3736. Therefore, the new heading is north 12.4 degrees west, expressed to 3 sig figs. And finally, part E, we need to find the magnitude of the plane's velocity with respect to the ground, which is technically the magnitude of our resultant. Again, we technically have the option of using the primary trig ratios, but that is not best practices. And the reason being is that our theta A has rounding error in it. So we really should work with Pythagorean theorem. And the reason why is because 150 and 700 are given values. There is no error in them. Now, using Pythagorean theorem, you have to have your wits about you. The vector equation is written R is equal to A plus B, where R is the resultant. Do not conflate the resultant with the hypotenuse. The resultant isn't always the hypotenuse. As you can see in our diagram, the resultant is not the hypotenuse. A is the hypotenuse. In our previous example, it just happened to be that the resultant was the hypotenuse in that case, which made using Pythagorean theorem fairly straightforward. But in this example, the resultant is definitely not the hypotenuse. So we have to start from scratch with Pythagorean theorem and isolate for vector R algebraically. Therefore, we start off with the following. The magnitude of vector A squared, which is our hypotenuse in this case, is equal to the magnitude of R squared plus the magnitude of vector B squared. Isolating for vector R, and now we can drop the extra notation. So we can just represent the magnitude of A. Vector A is just simply A squared like this. Bringing the B squared term over to the other side using subtraction is equal to R squared. Skipping 2 steps, I'm going to turn the equation around and isolate for R at the same time. So R is equal to the square root of 700 squared minus 150. The other thing you should note is I did not put a positive value, did not put a plus sign in front of the 700 or the 150. If you recall from grade 11, I usually indicate pluses and minuses for direction. So why did I decidedly not put the plus signs and the minus signs? Simple. We're working with the magnitudes, not the actual vectors themselves. So the magnitude of our resultant is 50 square root of 187, or 683.7397 kilometers per hour. Of course, rounding that to 3 sig figs, that gives us the magnitude of the plane's velocity with respect to the ground is 684 kilometers per hour. Moving on to example 2. A plane heading due south at 700 kilometers per hour is flying through a wind blowing at 150 kilometers per hour west 30 degrees south. Now, if you look, this is very similar to the first sample problem. The big difference, though, is the change in the wind direction. Everything else in this question is the same, and it's asking all the same things as the previous one, but the geometry is sufficiently different enough that the math that we have to pick is going to be significantly different. So let's just quickly do the given section. So the 700 kilometers per hour is related to the plane's velocity with respect to the wind. And it is 700 kilometers per hour, but this time due south. The wind's velocity with respect to the ground has the same magnitude as before. It's 150 kilometers per hour, but this time it's moving west 30 degrees south. So in part A, we're again looking for the magnitude of the plane's velocity with respect to the ground. Part B, we're looking for the actual plane's velocity with respect to the ground. So therefore, we're looking for the angle of the bearing. Part C, we're trying to see how far off course the wind blows the plane. So we're looking for the wind's displacement with respect to the ground. And we have a new number. Our time is equal to 2 hours. And then in part D, things change again. In part D, it again asks us what heading the plane must maintain in order to travel due south with respect to the ground. That again implies that we have to determine what the new heading is going to be because we now know what the bearing is, as opposed to part A through C, where we knew what the heading was. Now we know what the bearing is. So in part D, we're looking for the theta of the heading. And in part E, we're looking for the magnitude of the plane's velocity with respect to the ground. And let's just finish off our given section. So in part D, the plane's velocity with respect to the wind still is a magnitude of 700 kilometers per hour, but the heading is unknown, which is ultimately going to be our theta A. Actually, best practice is we'll just put a question mark there for now. And we lost one piece of information, but we gained something, and that is the bearing. So unknown magnitude for the plane's velocity with respect to the ground, but we know it has a bearing of due south. Just like before, we start with our vector equation. The plane's velocity with respect to the ground, which is our resultant, is equal to the plane's velocity with respect to the wind, plus the wind's velocity with respect to the ground. It is the exact same equation as before. So giving our vectors their short names, PVG is the resultant, PVW is vector A, WVG is vector B. And we're going to modify our given section accordingly. And we'll do the same thing with the required to find section. Next, we have to draw the vector diagram. So this case, we can start with vector A, which is 700 kilometers per hour south. We know the magnitude and direction. Now, if you notice, I started a little bit towards the right. And the reason why, because I know what's coming up, and that is vector B. So vector A has a magnitude of 700 and it's due south. Now let's take a look at our vector B. Our vector B has a magnitude of 150 kilometers per hour, but the direction is west 30 degrees south, which means that that vector is not playing nice. And since that vector is not playing nice, we need to draw our compass rose at the head of vector A in order to correctly draw vector B. Now, when drawing vector B, be cognizant of the fact that vector B is not only shorter, but its angle is more west than it is south, because it is west 30 degrees south. So when you do draw vector B, try to get it close to 30 degrees. Again, this isn't a perfectly scaled diagram, but it should be reasonably accurate. So there's our vector B and a magnitude of 150. And since it was west 30 degrees south, this angle here is 30 degrees. And again, it's not that important for you to carry all the sig figs on the diagram itself, just as long as the final answer is reported to the appropriate number of sig figs. And then finally, we draw in our resultant. That is theta r at the tail of the resultant. And do not forget to dash your resultant line. Now, a couple of things to note. This is a scalene triangle, so we can't use Pythagorean theorem. We will have to either use sine law and cosine law or component method. In this particular case, I would actually just stick with sine law and cosine law. And the main reason why is our first vector A is actually playing nice. So calculating the value for theta r is relatively easy. But before we use sine law and cosine law, we're going to have to find a few more pieces of information in order to actually complete this. One of them, of course, is we need at least one angle in our triangle. At the moment, we don't have any angles within the triangle. We just have this 30 degrees that is sitting between vector B and the compass rose. But we do know that vector A is traveling due south, and the angle between the south line, well, technically I should say this is actually the north line of the compass rose, and the west line, we know that this angle here is going to be 90 degrees. So this gives us a total internal angle here, and I'll call this angle capital R, of 120 degrees. Therefore, based on the information in the diagram, we have side angle side. This implies that we're going to be using cosine law. And as a reminder, the general form of cosine law is c squared is equal to a squared plus b squared minus 2ab cosine of angle c. So to find the magnitude of the plane's velocity with respect to the ground, or really just the magnitude of the resultant, using our letters, that will be the magnitude of the resultant squared is equal to the magnitude of vector A squared plus the magnitude of vector B squared minus 2 times the magnitude of A times the magnitude of B cos of angle R. Of course, now we can just drop the excessive notation and take the square root of both sides. So we get R is equal to the square root of A squared plus B squared minus 2AB cos of angle R. Substituting in, we get 700 squared plus 150 squared minus 2 times 700 times 150 cos of 120. This gives us a value of 50 root 247, or in decimal form, 785.812 kilometers per hour. Now, obviously, 50 root 247 is a better version of the answer in terms of error than the decimal version. However, it's still, and I'm using this slightly faded green here, because we are still subject to error, because again, we could have made a mistake in the equation above. So the values 700 and 150 are perfectly pristine. Same with 120 degrees. But this value for R, 50 root 247, is technically subject to error. And finally, our therefore statement. Therefore, the magnitude of PBG is equal to 786 kilometers per hour, rounded to 3 sig figs. Next, we have to find the angle of the bearing, or in this case, it's theta r. Now, to find the angle, we have the choice of either using sine law or cosine law. Sine law is the easier of the two laws to use. However, it is subject to the ambiguous case. So the only time it's dangerous is if the angle that we're looking for has the potential to be greater than 90 degrees. Well, based on our diagram, theta r, there's no chance for theta r to be greater than 90 degrees, and that is for two reasons. One, theta r is opposite side B, which is not the longest side, and in fact, side B is the shortest side. In addition, we already do have an obtuse angle, which is angle R, and you can't have two obtuse angles in a triangle. So using sine law is perfectly safe. So again, sine law is sine A over side A is equal to sine angle B over side B, which is equal to sine angle C over side C. So since we're looking for theta R is opposite to side B. So it is in this form. It's going to be sine of angle B over the magnitude of B is equal to the sine of angle R over the magnitude of R. But the thing to note is that angle B is theta R, because angle B is always opposite to side B. Therefore, sine theta R over B, dropping the excessive notation, is equal to sine angle R over R. So isolating for theta R, we're going to do a couple of things at once. So step one is I am going to bring the B to the other side. So I get B sine angle R over r, and the opposite of sine is sine inverse or arc sine. So substituting in, we have 150 sine of 120, and notice the value that I used for the resultant. I used the 50 root 247 as opposed to the decimal version, which was 785.812, and the rounded version to 3 sig figs is even worse. So best practices is to use the value with the least amount of rounding, which of course is our 50 root 247. Therefore, the plane's velocity with respect to the ground is 786 kilometers per hour, south 9.52 degrees west, rounded off to 3 sig figs. Part C. This is where we have to find how far off course the plane flies. So here we're looking for the wind's displacement with respect to the ground. And again, the reason why is because it is the wind that is blowing the plane off course, and however far the wind travels and in which direction tells us the amount that the plane is thrown off course. Since the wind is traveling at a constant velocity, we can use the constant velocity or constant speed equation, d is equal to vt. So the wind's displacement with respect to the ground is equal to the wind's velocity with respect to the ground times the time. Substituting in, that will be 150 times 2, so we get a magnitude of 300 kilometers. Therefore, the wind's displacement with respect to the ground is 300 kilometers to 3 sig figs, but the direction in this case is west, 30.0 degrees south. Now for part D. Part D is the situation now where we no longer have the heading. We're now trying to fix the heading so that we actually have a bearing of due south. So for part D, we're looking to find the new heading, which will be our theta A. Again, this would be a good time to restate our given section because things have changed. So vector A, which is the plane's velocity with respect to the wind, is still 700 kilometers per hour, but this time with an unknown direction, which is the theta A that we are trying to find. Our vector B, still 150 kilometers per hour, and that's the wind's velocity with respect to the ground, and it is west 30 degrees south. We lost the heading, but we did gain the bearing. So the resultant has an unknown magnitude, but we do know the direction is south. And just like before, the vector equation is unchanged. The plane's velocity with respect to the ground is still equal to the plane's velocity with respect to the wind, plus the wind's velocity with respect to the ground. Putting in our short names, except let's get the correct short names, resultant, vector A and vector B. There we go. And now the tricky part, drawing the new vector diagram. The main issue is we don't know the heading of vector A. So we can't start with vector A. So when we run in that situation, we follow the following set of steps. Step 1 is you always start with the vector or vectors for which we know everything. In this case, it is vector B. Vector B, we know both the magnitude and the direction. So we're going to start off with that. Now, of course, vector B is not playing nice, so that means we have to start with our compass rose. Now, I already kind of know which way this is going to go, but you kind of have to get the ability to map this out in your head a little bit to figure out where we're going to start. You don't want to start up here because we do know that the plane is going to be flying south, and likely, since we're trying to fight the wind that has a west component, the plane's heading is likely going to have an eastern component to it. Okay, so starting with the compass rose, I'm going to zoom in a little bit, and we draw our vector B. When you're making these diagrams, and since you have to label so much information, you're going to want to make them as big as possible. So labeling what we know, this is vector B. It has a magnitude of 150 kilometers per hour, and this angle right in here is 30 degrees. Next is you start with the vector for which you have the direction, and that is our resultant. So we know that our resultant is pointing south. And if you recall, the resultant has to go head to head with vector B. So I don't know how long the resultant is, but I do know that it is due south. So that's our resultant there. Make sure you draw the dashed lines. And then our vector A, there's only one way to draw vector A, and we know that vector A is tail to tail with the resultant, and it also has to connect to the tail of vector B, and that is our vector A right there. And this angle here is our theta A, and that is our heading. Again, we're going to be relying on sine law and cosine law, so that means we're going to need at least an angle here. Well, here's the thing. I have part of this angle, the angle opposite to side R. I have 30 degrees of it, but the remainder here, that is unknown. Theta A is also something that we're trying to find. So the only angle we have left is the angle opposite to side A. We'll call that angle A, and we need to be able to find that. In order to be able to do that, a second compass rose will help us. And when we do this, you can see that we have the Z pattern. And if you can't see the Z pattern, it is right here. That's an awfully large Z. All right. So because of the Z pattern, we know this angle in here is 30 degrees. And I'll just write Z pat there. But that 30 degrees is outside of our triangle. So this angle here, our angle A, it's going to be equal to 60 degrees. And that's because of complementary angle theorem. And that's because we know that in the compass rose, the angle between the north line and the east line is 90 degrees. So therefore, our 30 degrees plus 60 degrees makes our 90. Now that we have our internal angle of 60 degrees, we have enough information now to solve for theta A. And here's what we know. We have a side, its opposing angle, and the other side that is opposing the desired angle, which is theta A. So we can use cosine law. Not cosine law, my apologies, sine law. Important thing to note though, that theta A is equal to our angle B, which is the angle opposite to side B. Sine of angle B over side B is equal to the sine of angle A over side A. So therefore the sine of theta A, because angle B and theta A are the same angle, and that's equal to B sine angle A over side A, and dropping the extra vector notation. Isolating for theta A, we take the sine inverse or the arc sine of both sides, and we get B sine angle A over side A. Substituting in, we get the arc sine or sine inverse of 150 sine of 60 over 700, which gives us 10.695 degrees. Rounding off to 3 sig figs, that would be 10.7. Therefore, the heading is south, 10.7 degrees east. And finally, we need to find the magnitude of the plane's velocity with respect to the ground, which is the magnitude of the resultant. We have the choice of using either sine law or cosine law. Regardless, it's going to require the same information, but we still have to find our angle R in order to be able to solve this. So this unknown angle in here, that is our angle R. Well, before we can actually solve this, we need to figure out what our value for angle R is, which is now relatively easy to do, but we have to rely on this calculated value, which is subject to error because of the rounding, as well as the potential for other mistakes, but we don't have any other option. We need to use this value. And the reason being is that I know that this angle is 60 degrees, and I know the total angle inside this triangle add up to 180 degrees. So therefore, in order to solve for angle R using some of the interior angles of a triangle theorem, we will have to use the value for theta A. We don't have a choice. So moving forward, step one is we're going to find our angle R. And we know that our angle R plus our angle B plus our angle A is equal to 180 degrees. So our angle R is equal to 180 degrees minus our angle A minus our angle B. Now again, remember that our angle B is the same as our theta A. And we're just making that quick little replacement right there. And I should actually write SATT up here. So we get an angle R of 109.305 degrees. I'm not going to round this because this is just used for an interim calculation. And finally, using sine law to solve for our resultant, we get a value of 762.842 kilometers per hour. Therefore, the plane's velocity with respect to the ground is equal to 763 kilometers per hour, or I should say the magnitude of the plane's velocity with respect to the ground is 763 kilometers per hour to 3 sig figs. And of course, its direction is south. And that's it.